Hello, everybody. Welcome to the second taping of Dayton Dialogues with me, your host, Andrew Schrader, and Greg Loughnane. So we're both technically the co-hosts of this podcast, but what we're doing now is we're starting off interviewing each other. So take a look at the last video somewhere around here. That was Greg interviewing me. Now I'm going to kind of talk to Greg to learn more a bit about what his experience is and kind of what he can elaborate on for our viewers here.
Love it. I'm really excited for this, Andrew, and I just like to say to all of our viewers out there, I'm really happy to get started off with sort of learn a little bit about Andrew, learn a little bit about me. And so, who knows where we're going to get into today. But Andrew's driving the ship and I'm here. And I can't wait to get started.
All right. So what I want to kind of start with is to let you all know a little bit more about Greg. So Greg earned both his master's and PhD from Wright State University here in the Dayton area. His master's was in more mechanical engineering at Wright State, but his PhD work was in something very different. It's maybe not something that everyone hears: computational design and optimization. So we see that Greg here has this mechanical footprint. He also got his bachelor's in mechanical engineering as well. And so what you may ask yourself right away is, you're a mechanical engineer. What are you doing with computational design and optimization? So what I want to start with is kind of getting your viewpoint, Greg, on, as someone from a mechanical background and footprint, what was so interesting to you about pursuing computational design and optimization beyond your mechanical footprint?
Yeah, that's a great question, Andrew. And I think this idea of computational design is something that really, from a Dayton perspective, is sort of very, very much kind of is rooted in doing simulations for aerospace related structures, aerospace related things, and so really the tie there was with my dissertation advisor, my initial dissertation advisor, a guy by the name of Ramana Grandi. And he was very interested in sort of doing optimization simulations and uncertainty quantification simulations for things where, they had kind of wind tunnel tests. And these wind tunnel tests, maybe they cost $1 million for each data point. So he really wanted to do as much as he could on the simulation side before they actually went and did experiments. So really that group, that idea, that kind of track in the PhD program was created as a result of this interest in aerospace structures. And the other thing I would say is that it was a perfect match for somebody who was kind of getting his master's degree in how does finite element software work? How do these things actually operate? And then how can you then take that and make it more generic? You sort of bust out of the mechanical realm when you start to look at multi-physics simulations, like fluids. And then you have sort of the solids and the fluids. And then it's like, well, what about the electronics? And what about the other things that you might simulate? And so it became this meta-abstracted sort of computational design and optimization thing. But it really was rooted from the beginning in mechanical engineering.
Yeah, so just for me to add on to that, I mean, that's what I see a lot, is this initial background in one engineering discipline gives you a lot of perspectives on maybe a lot of the physics in that engineering discipline, but there are so many ways to employ those skills and knowledge that you learn in your undergraduate to maybe something even new, or just applying your expertise to something unique for graduate school.
Yeah. Well, and I would say that's exactly what I worked with some AFRL scientists trying to do. And it was very, very, very challenging to sort of force this thing that I was trying to do into this old framework that I had, learned and that I had come from. And really the struggle associated with that is what really started to pave the path for what became the rest of my still young career.
Hmm. And I noticed that you didn't just stop there. You're actually what I would call the lifelong learner. You know, you haven't stopped. You're currently, let's see, you're earning something called an NGA, or the next great adventure at Acton School of Business.
That's
Can
right.
you talk a little bit about that and kind of maybe how you believe that additional knowledge ties into what your background in more of the physics or mechanical engineering based sciences kind of ties into that?
Yeah, I guess in order to tell the story of the Next Great Adventure program, the first thing that I would say is they sort of rebranded it. It was an MBA for something like 20 years. This school created by these ex-oil billionaire dudes that kind of became fed up with University of Texas at Austin, and they kind of did their own thing. And they stood it up and they started cranking out all-star students. In the past few years, they dropped the price to the floor, but they got rid of the accreditation. And so they switched it from MBA to NGA, right? And so, but in order to sort of get to the point of how I got there, it's interesting to sort of stick with this idea of computational design and optimization. And really, I started to get more into this simulation world, more into the materials world. Because as you know, Andrew, it's like as a mechanical engineer, you often walk around and you say, I'm not a materials engineer. That's not my thing. Right? That's not what I want to do. And now I was one of those people. I was like, no, I hate materials, right? And then I end up getting a freaking PhD in materials, right? and it's like, God, it's like, that's just life, right? But, on some level, what happened was I get in the door, I wrote a proposal, it accidentally got funded. So I get in with these material scientists on base. And this was all through Romana Grandi. And so in 2011, it was sort of the first ever world conference. It was the first conference I ever went to. It was the Integrated Computational Materials Engineering Conference. And they said, okay, integrated computational materials engineering. The focus is on the integrated and the engineering. And that's what they said. And I was like, okay, like that's cool. So you're saying I don't need to be a materials scientist to play in this sandbox with you guys. And they're like, yeah, you can just be a computational guy. I was like, oh, okay, great. I'll just do that. And so I started to do that. And that was a space that continued to grow and really became hot towards the end of my PhD in about 2014 with 3D printing. Because 3D printing is that nice, beautiful mix of mechanics and materials. And then also there's really interesting simulation problems there. And so, I was really very interested in looking at what are people doing in the simulation, materials, manufacturing space. And of course, there's the Materials and Manufacturing Directorate at the Air Force Research Labs a few miles away. And I was working with those guys. So of course, I went to that conference. It all circles together. And so really what happened is I went from being this very researchy person to wanting to move towards more development and less research. And as I did that, as I continued to try to make that transition, I found it very, very challenging and very difficult. And I felt like I just didn't have access to enough resources in Dayton about who can tell me about more of the development, more of the commercialization, and who can tell me how to act like somebody from Silicon Valley, and who can tell me how to be this person that I want to be. I mean, and I couldn't find what I was looking for. And maybe I didn't look hard enough. Maybe it's been there all along. But eventually the Acton NGA program was the place that I did find those nuts and bolts. That education that I had always sort of felt was a missing component. And it allowed me to then, understand the lingo. It's all about lingo, right? If you don't know the words, you can't have the discussion. And so I didn't want to be afraid of having the discussion about cash, of having the discussion about how to create businesses, of having the discussion about, well, what's your intrinsic firm value, right? If you don't know the words, people think you're stupid for some reason. And, and then I was the stupid engineer that, thought, know more than the business guys, and the business guys think, oh, you're just a stupid myopic engineer. And so I really was focused on, I loved being a scientist, But I also saw where I could do, like Elon Musk is a scientist too, just ask him, right? I wanted to understand what was missing from the science, bench scientist point of view. And that I found it at Acton. I found it at Acton.
And so this lifelong learning, this additional, every time you're seeking a new question, you're trying to find a new answer and you're finding ways to learn more and educate yourself about these sort of things. And so our hope is that our viewers out there are doing the exact same thing for these topics here. So these are kind of ways for you to also kind of do this continued learning like Greg has kind of modeled for us here. And so when we're talking about kind of where you're taking these ideas and these questions, we see that you have done a lot, you've earned a lot of respect and development and research and commercialization related to a couple of topics. So I see you're a big player in advanced manufacturing. We have data science, educational technology, and entrepreneurship. So these at first may seem like things that are completely disconnected, but hopefully we kind of dig into a bit today and see how all of these things build up towards the Greg.
Well, and I would say I'm continuing to see too where all these things continue. And really the way I view this is I view these as pools, from whence the spirit of future Greg may come. Like, so you kind of have, entrepreneurship and educational tech, data science and advanced manufacturing. So what happens if you just mix all these together? And that's where future Greg is headed. But it took a long time for Greg to get this list of 4 relatively specific things to put together. And it took a lot, I would say, countless iterations to get there. And I think, so let's take it apart. I mean, we sort of talked a little bit about the entrepreneurship piece, right? What are we doing right now? This is sort of the educational technology piece that I'm so interested in is like, what is the best way to educate people, right? It doesn't have to be about 19-year-old students. It doesn't even have to be about other people. It can be about yourself, right? That's what we're talking about with lifelong learning. It's like, what is the best way to learn stuff and then to do stuff? And, I think this is a very fundamental question that I've just become absolutely enamored with. And, I always loved teaching. I didn't really know why, but it always gave me energy. And I always really thrived on it. It just never paid the bills, man. You know how it goes. and it's like, so I was always at this intersection of, well, how can I do what I love doing, but then how can I also pay the bills? And so that's where the research and that's where the entrepreneurship and that's where the development initially came in. But when we talk about advanced manufacturing, you can kind of tell it comes out of this, well, I'm on the integrated in the engineering, the mechanical and the materials. I'm the computational guy in the material scientist world. That's where I started. And that's where I am today, I would say. A lot of people think of me as a material scientist and, I continue to learn more about it, but I've met some really brilliant material scientists and I can't hold a candle to those guys, and so it's not that I'm not that, it's just that I know that there are people who really, that's who they are. And so, I can say that I'm not that, but I can also say that, this advanced manufacturing space, it's become so amorphous that it's really hard to keep track of. And is robotics in it? Is cybersecurity in it? What's in it anymore? Is the whole supply chain in it? So it's basically an integrated, industrial systems engineer, plus a materials engineer, plus a chemical engineer, plus a mechanical, plus an electrical, plus sensors, plus, it's kind of like this crazy thing. So, I keep aiming at it because it's one of these things that's a great source of lifelong learning. And it's sort of this infinite wellspring for me. And I think the data science piece, really, that's the buzzword compliant word of the day, but really it came out of the optimization degree, right? I get a degree in optimization in 2015. I write my first proposal. And then, NASA comes back and they say, hey, Greg, this empirical optimization thing sounds really good, but like, where's the machine learning, right? Where is it? And I was like, ooh, damn, I don't actually know what machine learning is, but I just got this PhD in optimization, and now they're asking me, and they just gave me money, so I guess I have to go figure it out now, right? And so that was when I started to say, oh man, like I really never even like really embraced coding until pretty late in grad school. And so I was still using MATLAB for pretty much everything in grad school. And by the time I got to the point where I was actually funded on my own project, being asked to do machine learning, I was like, man, I got to learn Python. Man, I gotta learn machine learning. Oh, then there's this deep learning thing. What is AI anyways, right? And so it led me down this rabbit hole to try to determine what does it mean to be a data scientist. And so, I think that's the right way to talk about it today. And so that's the fourth component.
So let's dig into this a bit more. So let's play a bit of a game here. Okay, we'll play Buzzword Bingo. So viewers, if you hear buzzwords, write it down. See how many buzzwords we're going to get through today, because that is a big component of a lot of these ideas. You hear Greg, talking through a lot of these big technical terms, these big buzzwords. So let's break them down a bit and get it from the expert. What are these major buzzwords and what do they mean? All right, so let's talk about kind of the first differences between some of these terms. We have advanced manufacturing, additive manufacturing, and subtractive manufacturing. Is that right?
That is right. And however, actually the most recent thing, if we're staying in up-to-date buzzword compliance here, then we should really add the new favorite category for everybody to throw in. You have additive, you have subtractive. So you're adding material from some piece of something, or you're subtracting material from some piece of something. And you could add stuff. It could be a repair, right? It could just be like you're painting something. That's an additive process. It could also be a complete 3D print, right? And subtractive, it's just you're drilling a hole, you're using a mill or a lathe to plane something or to roll it down. I mean, you could be using anything to cut something. I mean, cutting vegetables in the kitchen is a subtractive process. But I think this third one that people have started to talk recently about is deformative. And they add this deformative piece in because that sort of rounds out the rest of the classic materials or manufacturing processes.
Is that like bending processes? Is that like deformative?
Yeah, it's kind of like it's like, how do you make giant blocks of steel, right? And it's like, well, you kind of throw a bunch of pieces of metal from the scrapyard in a giant pot, you boil it up until it's lava, you dump it in a mold, and then you like bang the hell out of it. And then you maybe deform it. And that's sort of forging, right? Is deforming, right? Or if you're rolling the shit out of something, then it's deforming it. Or, basically anytime that you're sort of controlling the substructure, that sort of micro level, millionth of a meter level structure of something in a specific way. And so, that's the third one. But, I think additive and subtractive, in terms of material addition, removal, that's pretty also, it's pretty comprehensive.
So I guess, what is advanced manufacturing, and how do these other terms even fit in? Do they even fit in, or is it?
Right. It's this new abstraction, man. That's what it is, and it's this new like made up story. Let's say, in some sense, it's kind of just like, because even like 3D printing, right? It like everybody was like, okay, 3D printing, right? And that was cool because we had 2D printing. You click print, and then pop out comes the paper. Okay, can I click print and then pop out comes the part? And so people are cool with that. And then there's this idea of an additive manufacturing process. That was sort of a construction thereafter too. It's like, okay, so we've got 3D printing, but then we have these other things that we could do. And so where does it end? It's like, well, it doesn't really, like I said, painting, right? Nobody talks about painting as the additive process, but it is, right? Or nobody talks about shaving as a subtractive process, but it is, right? It's like, and so, but when we talk about materials and materials engineering, I think that when we talk additive, it's really this thing that brings materials and mechanical engineers together like nothing else ever has in the history of all materials and mechanical engineering. And so in that sense, it's one of the most important things and the most important breakthroughs that we've seen. Because this is something that I've seen at university after university, even in my short 10 years being in grad school and beyond. I mean, is that people are coming together like people that just never really wanted to work together are coming together like I've never seen. And that is a uniquely additive thing. And I don't know what the secret sauce is there, but if we could replicate that in a couple different industries, and I think that's what's happening with this abstraction of advanced manufacturing. We're sort of folding in, okay, well, what about the cybersecurity guys? What about the supply chain guys? What about the electrical guys? What about, because it's all sort of rooted in this idea of everything comes back to data, right? So if you have a company and and it comes back to entrepreneurship from my perspective, right? If you have a company or if you have any, bureaucracy, institution, government, academic, whatever, you have a bunch of data about all sorts of things, okay? And what should you do with all that data to make sure that your company keeps going and growing and thriving? It's like, well, you should make decisions with it, actionable decisions. And so when you start to play with this idea that, well, as you abstract and you abstract and you abstract and you abstract, there's one giant place, the warehouse, where all your data goes. And that could be materials and manufacturing data. It could be operations data. It could be HR data. It could be any data. But if you just sort of start with the materials and manufacturing people coming together, and the data needs to be the same data to solve the additive problem, I see sort of the hierarchies of data coming from all places in the business and all places in the supply chain, really. When you talk about distributed advanced manufacturing supply chains, all of it is coming together and it's sort of being abstracted just like programming is. Okay. And just like the data, so data science is just sort of data programming. And it's like, this is where the world is heading, and these abstractions that we have to keep up with. And with new abstractions come new buzzwords that are harder and harder to get to the bottom of.
So it sounds like we can just harvest data on data, whether it's, specific processes, let's say if we're manufacturing a part, what's the temperature of the part? What's the pressure of the atmosphere that the part has been made in? But it could be, the time, it could be the specific motions, all sorts of different data that can go into it. So now's when we go on to the next step of Buzzword Bingo. How do we cut through the data, and how do we do optimization? And what is optimization? And so Nick, what actually I would love right now is a little bingo card that you can put together every time a buzzword comes up. Stick it in that bingo card. And then maybe,
yeah. So I think that's a great question.
Nick's our producer. He's the one helping.
Yeah. Nick is a great producer. Yeah. And he's nailing it for us. But I think that in order to like harvest all the data, right? And in order to say, okay, well, what does it mean to optimize based on all this data? Well, you have to first say, well, okay, what should I even be spending my time doing, right? What should I be aiming at? And what position am I standing in that allows me to make that decision? So if I'm a company CEO, then I have a bottom line that is very obvious, that I want to keep my people employed. I want to continue to grow the company. I want to continue to have an impact, create more value, deliver it to my customers, my shareholders, my employees, everybody. I want more value creation just everywhere. If you're just an engineer or a manager in a department, then you've got a different perspective. And you say, okay, well, optimization of what I'm going to do with my data means something different to me. And in fact, it might not even touch the sales side of the house at all. Maybe it's completely in the operations side. Maybe you're a process engineering manager, and your goal is to optimize the hell out of the production system that's in there, cranking out whatever it is that you're cranking out at your company. And so your optimization might be maximize the number of parts coming out of the end of the machine per day or per month or whatever. And so then you're on this sort of like Eliyahu Goldratt, The Goal Status, which is a very famous book that I never actually heard of until I already had a PhD and I had gone to business school 5 years later. If you're a budding scientist in manufacturing out there, read The Goal, please, because every CEO in the world is going to tell you to do it. But anyways, if that's the, and I discovered this guy and I was like, I got a PhD in optimization and nobody ever told me about this guy. I cannot believe this. But this was a scientist guy, cum entrepreneur and very, very wealthy business guy. But he wrote this novel and it's all about finding the bottlenecks in the process. And so to optimize a manufacturing process might be to find those bottlenecks and to alleviate them and to say, okay, how can I make sure that I get the most throughput? And he defines throughput some specific way. Other cost-based accounting, ways of doing it would say, okay, just maximize the number of total widgets. Bottlenecks be damned. And so you end up with these giant work in process stacks. And so if that's your job, that's the way you look at the world. But it depends on where you're at. And so you can't say that there's one right answer to optimize the data based on one specific thing. What you can do is you can say, and this is what people should do, is you can say, okay, I'm me. This is where I am. This is where I've been, and this is where I want to go. And this is what I should do with my job right now to help me figure out how to get there. And if you can do that and you can frame your life like that, then you can say, how could I take it to the next level faster? And I think that the data and the tools that are available at your fingertips all the time and getting better every day, they can come in and they can help you do that faster. But if you don't know where you're going and you don't know, and you don't have any intuition about how you might get there, then you're sort of screwed on the data thing. And there's some deep reasons for this, because when you have a software engineering problem, it's perfectly scoped. You build this just like this, and then when you're done, you're done. Check, 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 check. Does it work? What goes in? What comes out? Everything's the same. When you solve a data science problem, you're sort of at the mercy of the data. And so, there was a great line from Peter Wang, the CEO of Anaconda, on a podcast I listened to recently. He's talking, data is just frozen models. I love this idea. It's just, data is not like software, and data is just frozen models. And it's like, why is it a frozen model? Well, because the camera that took the picture of your data has a bunch of sensors inside of it. It's a whole physics-based model way of capturing the universe in and of itself.
I see.
And so this idea that you're constrained by the way the data was even captured, and so you have to think sort of beyond the data first, and that's sort of where you're headed and what you care about in the context of your company and your role and all of that. And then you have to think, okay, well, within that intuition of mine, is there data that exists or that could exist easily that I could then use with these newfangled prediction models to be able to predict something that might push the needle forward faster? And it's very, very hard to find these situations where you actually are doing something that's not just a research project. It's very, very, very hard. And
so what do you mean? What do you mean by that when you say not just a research project? Can you elaborate on that a bit more?
Yeah, so in research, when you basically do a whole bunch of things that don't work, and then every once in a while you do something that works,
Yes,
and then you're like,
that's
oh,
all research.
That's the thing. That's the thing I need to take forward with me, and the rest is deadwood, right? And so the rest I'm going to let burn off, and if somebody wants to pick it up for some other reason in the future, at least I published it and I moved on with my life. And I think that's what happens with data science too, is that where what you're doing is you're doing research. I mean, fundamentally you're searching and you're researching, and then you're searching some more. And so what you then have to do is you need to say, okay, did this tiny little data model that I put together real quick, did it work for the thing that I thought it could work for? And it's like, no. Okay, then move on. And did it work for something I could still use? Maybe, but then you turn into this solution looking for a problem, and that's no good, right? What you want to do is you want to start at the problem level with every new data science project, and you want to fail as quickly as you possibly can. And so there's a lot of people failing. There's a lot of people failing very quickly. And then the other thing about it is that it's fundamentally a research sort of department, your data science department. So you direct a research lab. You know what I'm talking about. It's like, just because one project works out doesn't mean you get to keep turning the crank on it, right? Because that has a finite life, that project. And so in data science, you have this thing where the accuracy will be increasing until it gets really, really good, and then it starts to sort of level out. And so you're putting a ton of money and compute resources into stuff that you're not getting very, very big incremental returns on. So what's the solution? Well, you go back to step 0 and you create a new project. And so you have to do this, and you have to have a pipeline of projects approaching this asymptotic accuracy and business value, and you have to be this infinite generator of small wins. So if you don't do that, then your data science or your research program dies, right? I don't have to tell you that. And so it's a thing that people haven't quite come to grips with yet. Everybody wants to look at it as software engineering, where your 1,000th, iteration is the same cost as your first. And it's just not this zero marginal cost thing that we're doing in data science.
So let's talk about some of these tools that you use to parse through the data, but then also to determine, when am I approaching my asymptote, right? When does this no longer worth my time and effort, and when do I start something else? And so some of these tools seem to be some more buzzwords here, right? We've got artificial intelligence. We have machine learning, the one that you had brought up earlier with NASA. So I am not in this realm whatsoever. Do I actually use artificial intelligence and machine learning without me realizing it? Or is it like a special, its own skill set? Like when I fit models to chemical kinetics, I am optimizing a model to my data. Right. So I'm trying to minimize the error between my model and my experimental data. What is that? Is that machine learning? Is that artificial intelligence? Or is that just lucky?
I mean, this is a great question. I would say if you're submitting a proposal tomorrow, put them in, put the words in, man, because I think you hit at least the lowest bar. Okay. Because so there's a difference between sort of like classical machine learning and deep learning. Okay.
That's deep learning. Obvious. That's another one.
That's another one, right? That's an obvious one. But deep learning is just one sort of machine learning architecture that's very specific and has been found to be very, very good at some things and maybe everything, according to the guy that invented it recently. But that's a rabbit hole we're not going to go down today. I mean, I think what's less clear is, well, what is the boundary between statistics and machine learning, right? Why is it that, because it used to be, before data scientists was a thing, the statisticians would get job as quants on Wall Street. And this was sort of the beginning of the data science stuff. And so like now everybody wants data scientists, but they're statisticians. And that's where most of them started. They started in statistics department, messing with one of the tools. It's a programming language called R, and it's just the letter R. And I used that when I was getting my graduate degree, because I had to take a bunch of statistics classes, and I didn't really like using it at the time. I also used MATLAB, and it wasn't as popular back then. And then, so you kind of have this weird thing where a lot of people will say machine learning is just statistics. It's just, I'm doing a linear regression. It's a least squares, right? It gets the least squared error, that's an optimized result, isn't it? And it's like, yes, it is. And the other interesting thing is that in classical optimization, and I would say classical optimization, let me frame this for you, is it means people who never thought that what the computer scientists were doing with all the data would ever freaking work. That's what it means, okay? It means that, so I had a bit of an old school professor back in the day, and he was not into this whole data thing at all, okay? And at that time, the way they talked about it was they said, well, these data scientists, there was no data scientist term back then. Well, the computer scientists that want to throw a bunch of data at problems and find magical answers to them, right? They're idiots, because those problems are non-convex. And a non-convex problem is one that doesn't have an obvious solution. And that's an oversimplification, but if you consider sort of, two-dimensional space, and then you have a three-dimensional space, you draw another axis through it. Then you have a four-dimensional space, five-dimensional, you can't visualize it anymore, n-dimensional space. In that n-dimensional space, there is one single best answer, okay? Mm. The old school optimization thinking was, if there's one single best answer, I can find it, right? If there's 1,000 best answers, then it's not a problem that I should ever consider solving, because it's intractable.
Okay.
For a number of reasons, computationally, physically, you just need to reframe the problem so that it's convex. And so that's a decent way of proceeding forward, right? And that's how simulations work, by the way, but that's, a rabbit hole in and of itself. And so I think that this idea that you have to have convex problems became something that, with GPUs and with computational processing power and with the amount of data that we have all the time, no, we don't need convex problems. We can get non-convex problems and find even non-perfectly optimal solutions, and they work just fine for creating lots of value in the world. And that's where the old school and the new school really separated. And when that became clear that that worked, everybody was like, oh, damn. And that's when, sort of to bring this artificial intelligence piece in, that's when the artificial intelligence folks, where originally the artificial intelligence community was on this sort of if then, else if then, else then.
Logic blocks, logic maps for.
Logic maps, logic trees, very logical, very orderly, it's completely defined by humans. And it's completely defined by subject matter experts. And, you're deep down in the if-then nested loops to make decisions. And that worked pretty well. But some people spent their entire career developing these loops, and you kind of got lost in the land of the loops there for a while. And computational power wasn't what it could have been. And, it wasn't what it was going to be. It was what it could have been, but as it got better and better, these things that people said were intractable became more tractable. And so as we started to realize that our fundamental axioms and assumptions that we were making about what does it mean to optimize something had to change, they changed very, very rapidly. And when that happened, that's when the deep neural nets said, hey, we just outperformed your rule-based thing. Like, sorry, professors, I know you spent 20 years on that, and we're kind of coming in like training this model in a week and beating yours, and like, but hashtag thanks for all the hard work and helping us get this pumped up to the point that we could have done this now, right? And
so it sounds like there is a very distinct divergence between artificial intelligence and machine learning. There's, if I'm understanding this right, there is this kind of two different schools of thought. One's more of this logic-based if-then, and the other is maybe more of this data science, this data mining, and letting the machine or the code find its own way. Am I understanding that right? Is that a good way to describe it, or did I just whiff on that?
I think it's a good start. I mean, okay. So the first thing that I would say to couch this a little bit more is to say artificial intelligence is the meta abstraction. So it's basically everything that's not just natural intelligence, right? So machine learning is included within the artificial intelligence. But when you talk about the origins of these things, they had clear and distinct boundaries then. But as we kind of discussed earlier, right, as we move forward with this technology and with this crazy world that we live in, things get abstracted, right? And as they get abstracted, they become more and more alike to other things that were maybe in dimensions that weren't even tangential to where we started. And so this idea that artificial intelligence is the big circle, machine learning is inside of it, deep learning is inside that, that's the sort of agreed upon standard thinking about this. However, okay, when you start to talk to the people who maybe have studied the concept of learning, like this is what actually people who have research, who do research in education, in adult education and things like that, that's what they study. Like, what is learning? What does it mean? And like, so you have this convergence of that community with the robotics community. And then you sort of have this idea that so now what does it mean for a machine to learn? And so then machine learning is in some sense abstracted from artificial intelligence. And so you have these different dimensions that you can view things in. But I would say for the computer scientists, the engineers out there, the right way to sort of talk to your boss about it today is to put AI, machine learning, deep learning. And I think moreover, the other key categorization that I would encourage you to think about is you have sort of the we know the answer things. And that could be rule-based if then, but it could also be a simulation. It could also be a finite element model, be a fluid structure interaction model, be a multiphysics cosmol model. It could be anything that you're assuming that you're in a bounded space that you know. And then on the other side, you have the data defines the space. And so when the data defines the space, whatever that camera, whatever time and length scale, whatever exposure time, whatever pixel size, whatever time and length scale your data is collected at, those are the physics that you're capturing. And maybe they're beyond your understanding in what you could do in I know the answer model. And so how much room is there to play with? And how can we start putting these, you can use one model to generate data and plug it into the data models. And so we get these weird abstractions as we move up and up and up and up, and it becomes, nearly impossible to say that there's a definitive right or wrong answer to these questions. But I think they're great questions to be asking. And I think you're exactly right. I mean, I think that there is a difference between machine learning, sort of think data, and classical AI, sort of think rule-based, and I think that's an okay thing to think. But the thing that people do now is they say AI powered everything. Everything's and in some sense it is. It's like trying to answer the question, what is programming? What do you mean? My program, the program I'm in, the program, the program that you put your students through, the program that Zoom uses to program whatever Zoom does. It's like, what is programming, right? It's like, I don't know, it's like nobody really knows anymore. And so when you get to this level, it becomes very, very difficult. But AI powered is used for everything. You are using machine learning and AI powered things every day, all the time, just like everyone else in the world. And I would say you're also doing machine learning and AI powered things in your research. But if you
it makes me feel good, because when I'm writing a proposal, I can be like, check out this machine learning that I got going on.
Yeah. But if you were writing that, then I would say, come to me and let me tell you some more words that are more specific to put in there that people will say, ooh, yeah, I'd really like to hear about that. And if you did that, that would be really cool too. So it's not enough anymore in 2020 to just say that. But it's technically, a lot of people have asked the question, because it's really funny, right? Here's an interesting sidebar here. It's like when you have a small model, so in order to build a big system, you build a small system first and then you scale it. So when you have a small model, you can do a really, really complex model on it. You can do like nonlinear simulations. You can do all sorts of crazy stuff. You can do anything you want because you have time and the computations are not going to take basically for the rest of your life until you die, right? And so you can make your model really, really complex. And so, but as your data scales up and up and up and up, and let's say you connect it into the web, and so you're getting new data every day, and you have to retrain your models every day. Well, now if it takes 8 hours to train your model, the day's already done by the time.
Oh, I see. Yeah,
so
that could be a problem.
Yeah, so what you end up with is you end up with these great fancy complex models for the small system. But then the scaled system gets implemented in such a way that all you're doing anymore is linear regression, right?
Oh,
and, and so it's the same thing with computational simulations, right? Because you can do nonlinear stuff, but nobody does that in industry, right? Only grad students do that in grad school. And the reason is because you have to do stuff quickly in real life. And so this is where the whole, if I'm doing linear regression, isn't that machine learning? It's like, yeah, it is, right? And actually at scale, that's how it's implemented a lot of times. So technically, yes. And so, keep it up, Andrew. Keep those machines learning, man.
All right, so I am now a AI/machine learning guru as well.
100%. Yes.
Awesome.
Yes. It's all, hey, this is what I love to say, right? Subject matter expert is a state of mind, right? It's not a real thing.
All right. So for subject matter expertise, I want to pose a question to you. And so I want to see kind of what your experience allows you to kind of figure out maybe what is the next frontier with regards to optimization, machine learning, and artificial intelligence in the sphere of advanced manufacturing.
Yes,
Where do you see this development going? Or what are you passionate about for pushing this frontier?
Yeah, right. Because those questions are intrinsically linked, right? I mean, like I can't speak to things that I've never really spent time on. And in order to spend time, I have to be passionate. So I think that that's a great question. And it's a question that I'm asking myself every day. And it's something that, I think that what's happening is as additive manufacturing, 3D printing is being sort of abstracted into this part of the advanced manufacturing supply chain thing. People are realizing, like my buddy, Chris Collins, who I hope to get on the show here in just a few shows. He's a local business owner. He's got 20 employees now, and he's absolutely crushing it. Cannot wait to hear from him. One of the things that he taught me is that, so he runs a 3D printing business. He creates medical device implants. And he taught me that, yeah, but the 3D printing process is only one piece of my final product, right? Like it's just one machine in the line of machines. Like, and so people are now realizing that, well, one company is just one company in the network of the supply chain. And so people are trying to now, and then people are saying, well, manufacturing materials data is just one aspect of the data along my enterprise planning resource data management system. And so, the Air Force's terminology for this is along the digital thread of a part or of a more complex system. So
is that like a life cycle analysis, like lifetime, or
it's like life cycle analysis. It's like the predictive maintenance predictions. It's like think of I always like this idea. I forget if it was Boeing or one of the other big OEMs that talked about this, but atoms to airplanes. If we could simulate atoms all the way up to the entire airplane, right? What would that computational model look like? So, so the digital thread is sort of like data to get you there, and then also to connect that entire physics-based simulation model to the ground, to real people, to the people working on it, to HR departments, to everything else in the world. So I think that in the context of the big picture of data, you sort of have to consider all of that. But in the sub-context that I'm most interested in of of advanced manufacturing, what I'm seeing is I'm seeing the additive community that has just really blossomed in the last 5 years. I'm seeing them start to realize that the best additive applications are ones that additive is only a component of everything that's happening in just a larger process in a company or as part of a larger supply chain network. So I think it's all about where does 3D printing actually fit in for you, for your future, for your company, and in the larger network of, let's say, in your state, in your city, in that manufacturing, especially in Ohio, in the aerospace corridor here from sort of Toledo down to Tennessee, right? In this space that we inhabit, aerospace manufacturing is huge. So that's sort of the network that I'm always envisioning. And that's the one that I'm hoping to really make an impact on and try to push forward faster than some of these other areas of the world, hopefully faster than all of them.
Yeah. So I also like to kind of maybe have you explain something to me a bit more.
Yeah.
And that is, I mean, everything that you've talked about seems to be towards innovation and optimization of, companies and processes and kind of overall how we do things to make some sort of impact in the real world, the business world, our everyday world. So there's a word that keeps popping up with a lot of our conversations outside of this podcast, and that's entrepreneurship. So another buzzword.
Yeah, that's for sure.
What
Oh man.
is entrepreneurship?
Oh yeah, God. Well, I mean, so I would say I'm less qualified than I'd like to be to answer this question, but I'm going to attempt it anyways. I can tell you what it's not, okay? And I can tell you that there are people that have widely varying views on this subject. So, for example, some people will tell you, Greg, that cute little consulting business that you created, that you just did defense contracting work with, and you basically bought yourself a job and you never scaled and you just continue to kind of use it for whatever. And, that's not entrepreneurship, right? Because you can't build a company, you can't sell it. It's never not going to be yours. You didn't systemize it, you didn't systematize it, you didn't do all the things you need to do to make sure that it can scale and be sold later. Okay, so that's one school of thought on entrepreneurship. If you're not doing something so that you're actually going to scale it and grow it and sell it, and because if it's not growing, it's dying. If it's not growing, it's dying, right? Then you're not an entrepreneur. Okay. But then there's this other school of thought that says, well, if you want to be self-employed, that's not a self-employment trap. That's just you doing what you want to do. And it doesn't matter if it's just you doing what you want to do, as long as that's actually what you want to do. So go ahead, do you, man, And there's people that say you're an entrepreneur too, right? So I like to draw the distinction between sort of entrepreneur and then serial entrepreneur, right? Because the serial entrepreneur is somebody who's interested in growing new things, in scaling them, in creating value, in handing them off to others, in doing this sort of very entrepreneurial stuff, nonstop, maybe forever, right? And then, but I would say then there's this idea of intrapreneur. And intrapreneur is this idea that you're going to go into a company like a GE, like a Boeing, like pick your biggest, like a government, like a federal government. This is the lean startup way. The Eric Ries, his newer book talks about. He went into the federal government. He ran it like a startup. What he was doing had great success. This is the sort of entrepreneur in residence title that we see so often now, where a successful entrepreneur will come into a bigger thing and then fix up, shake some things up, maybe get some things happening. And so, and I would say too, I mean, what gave me the skills to move into entrepreneurship was doing research, right? Because what do you have to do as an entrepreneur? you have to search and you have to research all the time. Search, search, right? And it's like, and then you have to go with it and you have to do that thing and you have to see it through. And it's very, very similar to what happens when anybody creates anything. So I like to think of it as more of a, I like to abstract it even further than entrepreneurship. I like to think of it as creation. It's sort of like the artist. You might say the artist that just makes paintings, but doesn't sell his paintings. Is not an entrepreneur. It's like, I don't know, there's a school of thought that could easily say, just for creation, you're sort of entrepreneurial and you've got that mindset, but you sort of want to be able to bring it together and you want to be able to say, okay, yes, I can create the technology. Yes, I can create the piece of art. Yes, I can do this. What is the thing that's actually delivering value to the world? And if you can talk to people about that, you can say, hey, I'm doing this thing, and this is why I think it's creating value. And you can get people to agree with you. I mean, now you're cooking with gasoline. Now you're a hell of an entrepreneur. I mean, but if you're even on the path to that, I think that what you're doing is developing that essential growth mindset of I'm onto the, like fundamentally to me, entrepreneurship is knowing that you're going to fail and being okay with it, knowing that you're going to go after things and knowing that you're not going to look for a time where you get to stop growing. Like that's what entrepreneurship means to me. So I don't think everything that I know and all the people that I've seen that there's a right answer to what is entrepreneurship. And it's the same as all these other crazy buzzwords we're playing Buzzword Bingo with.
Right, exactly.
It's even more meta. It's like the most meta. It's something like optimization too. I mean, if you're trying to optimize your own life, the life of yourself, the life of your family, the life of your community, the life of people around you, then you're a freaking entrepreneur, man. And that's sort of where you get into these interesting ideas of, well, now the new buzzword is social entrepreneurship, right? What does this mean, right? Well, it's like, what does it mean? It's like, well, I mean, what is a nonprofit then? I mean, what is somebody who starts a nonprofit? Is that an entrepreneur? Is that sort of a social entrepreneur? It's like, so there's all these different ways that don't have to be so associated with like getting huge capital and huge returns and becoming a millionaire or billionaire, quadrillionaire or whatever. It doesn't have to be that. I think it's simpler than that. I think you bring it back down to creator, you bring it back down to growth mindset, you bring it back down to, are you trying to optimize your own life and the lives of the people that are most important to you? You're a freaking entrepreneur.
And I mean, so building on this idea of entrepreneurship, I mean, we're here in Dayton, a city that has such a rich history and tradition of entrepreneurship. So for some of the viewers out there who may not realize this, Dayton, this is where the Wright family was really based in developing all the technology that they investigated. Bicycles, including their flyers. Hello, we're the University of Dayton Flyers. And then Wright State, which is where Greg went, the Wright family, W-R-I-G-H-T, both brothers and their the sister as well, all great innovators and entrepreneurs. We have the Kettering family as well, big entrepreneurs here. We have the Air Force Research Lab in Wright-Patt Air Force Base, more entrepreneurship. So we're in a rich, we have a rich tradition that we can follow up on.
Yeah.
So what opportunities are available now? That's all history. That's all tradition. Right. It's wonderful to learn from that. But where do you see students here at the University of Dayton getting involved in these types of entrepreneurial ideas?
Yeah, I think that's a great question. And I think, to add to your point, it's like, airplanes, right? Like the pop top can, national cash register.
Oh, yes.
These are great innovations that came out of Dayton. But guess what they sound like? They sound dated because they are. So what does the future look like? Well, The future, the thing about Dayton that I think is so incredible is that we've got the brilliance all around us if we could just figure out how to leverage it. And so what I mean is we've got the Air Force Research Lab. This is maybe one of the very, very, very few top premier research institutions. Basically, it has everything in the universe that they literally study everything in the universe. There, literally. Okay, yeah. Literally. They see atoms every day. Okay, like they do crazy stuff there every single day. There are nothing but brilliant scientists that love what they do there. Okay, but brilliant bench scientists are not entrepreneurs. And so what the entrepreneurs in Dayton need to do is they need to leverage all of these resources. So the University of Dayton is a great resource. The University of Dayton Research Institute does $150 million in research a year, right? The Air Force Research Labs does $5 billion in research a year, okay? It's like, how are we not leveraging this? And the answer is, well, because most people end up aiming at things that already exist, not things that don't. And so most people end up saying, oh, the base is like a great employer. I could potentially work at the base. Yeah, you could, but you could also leverage the base and all of the brilliant scientists and do your own thing, right? And be the next Wright brother, be the next, person that develops the game-changing technology that really brings up the city. And I think, the problem with having such a great, successful government lab is that it attracts everybody to it and nobody wants to do anything else. And then, the stuff, and it's literally inside of a fence, people. Like, you can't get in if you're not a citizen, if you're an international student, like you don't have that opportunity, right? Unless you're going to wait a long, long time. And then the stuff that they want to do, it's fundamentally Department of Defense stuff. But the science that they're doing is not connected to anything. If you need a brilliant scientist, you can find a brilliant scientist for anything in the universe that you can imagine in Dayton, Ohio, okay? Your problem is find what you're passionate about, okay? Then work with someone like me, someone like Andrew, someone at UD to help you match the technology that is going to help you solve that problem to what you're passionate about and the problem that you want to solve. Once you match that, we can help you find a brilliant scientist. We can help you find capital. We can help you find space. We've got a burgeoning downtown. I mean, when you Google Dayton, Ohio entrepreneurship scene in a few years, you're going to see the arcade. Dayton's got a foothold in this. It's a great, beautiful old building. It's going to be the place to go. And it's opening up in just a few months here. Downtown has really seen a revitalization in the last few years. And we're really getting, I heard the other day, I really liked this from another UD guy, Vince Lewis. He said, I believe Dayton is about 10, 15 years behind Cincinnati. It's like, right on. Let's get to work, man. Cincinnati seems a lot bigger than Dayton. It's like, but it doesn't have to seem so much bigger. And we need people to get excited about things, that want to change the world, that want to do stuff outside the UD fence, outside the Air Force fence, outside the UDRI fence, and really bring up that local industry. And the only way to do that is to get passionate about something that nobody's going to tell you what it is. So that's what I would encourage all of our viewers out there to do. Find something that you can get passionate about that nobody else is really that passionate about, and be okay with being out there on the ledge by yourself. I mean, Andrew, tell them, right? Doesn't matter if you want to be a professor or an entrepreneur. You got to be okay with being out there on the edge, doing your own weird thing, right?
Oh, definitely. Definitely. Yeah. I mean, my work, I'm trying to leverage solar thermal resources to do pretty much anything you can imagine. I'm trying to find ways to do that sort of work. And so what I want to do now is go ahead and wrap this up. Greg, I want to thank you for talking to us a little bit more, for us to get to know you a bit further so we can understand kind of as we continue with these podcasts, continue co-hosting, kind of where our perspectives are coming from. So thank you again, everyone, for watching. I appreciate all your help. Thank our producer, Nick, for doing all the work that he's been doing. And that's where we are for episode 2 of our Dayton Dialogues. So thank you all again.
Till next time.
Till next time.
Yeah.